Okay, so for the do now, for number one, this is a multiple choice question that is related to alloys. So which of the following diagrams best depicts an alloy of nickel and boron? So when you're looking at representations of alloys, you want to compare the sizes of the two atoms that you're given. So if you look on the periodic table for nickel, which is in the fourth row, boron is in the second row. So nickel and boron differ greatly in size. So we would expect the nickel atoms to be larger than boron. The only representation that has the nickel atoms larger than boron is A. So we'll talk about why the other ones aren't correct. So if it's an alloy, more than likely we're going to have some sort of lattice, so some sort of crystal structure. And an alloy typically means that one either replaces another or gets filled into the holes. So B is actually showing a compound of Ni and B. So it's each one of these is a molecule of Ni bonded to B. So that's not true. That would be an intermetallic compound, not an alloy. C shows a substitutional alloy. So if instead of nickel and boron, this was two metals that were similar in size, we would expect C to be the answer. But because nickel and boron are different sizes, C cannot be correct. And D actually represents an ionic compound where the cation and the anion are similar in size. So the only answer that makes sense for number one is A. Nickel and boron create an interstitial alloy. So A represents an interstitial alloy. C represents substitutional. So one is A. Number two, which of the following is the strongest type of interaction that occurs between the atoms within the circled areas of the two molecules represented above? So we're looking at the interaction between this hydrogen and this oxygen, this hydrogen and this nitrogen. So notice that there is no bond in between. There's no single line or double line for it to be a bond. So A and B, we can cancel out. In order for it to be a bond, like this is a bond. Right? This is a bond. There's no bond in these circles, so it's an intermolecular force. So then we're between C and D. So we have to look, remember, for it to be a hydrogen bond, the hydrogen needs to be covalently bonded to NO or F. So this hydrogen is covalently bonded to NO or F, and the H is attracted to an O. So this is a hydrogen bond. This hydrogen is covalently bonded to N, and it's attracted to another N. So that's also a hydrogen bond. So number two is C. So one is A, two is C. So that was it for the do now today. Again, we're going to be going through number 23 of mastering together. So you'll want to make sure that either you have mastering open so you can see your numbers, or you're going to just want to make sure that you make yourself a note as we go through the question that the number is going to be different than what you have. So before we jump into number 23 today in class, that's all we're actually doing together is 23. If a lot of people have the same questions about a different mastering problem, then I'll just pull up a piece of paper on the document camera and work through that problem on Google Meet as well. And once we go through number 23, you're just going to have time to work on mastering. So you can work on 17 up through number 30. If you have questions, you can jump back in the Google Meet and ask, or you can unmute and ask. I would recommend while you're working today, just leave the Google Meet open, stay muted. But I would leave it open just in case people have questions and then you have the same question. Then when I talk about it one time, you're not, somewhere else, not on the Google Meet. Over the weekend, so you will watch video 14. It's already up in Edpuzzle over the weekend. So by Monday, you'll want to make sure to watch that. Continue working on mastering. The schedule for today is a little bit different. We're on an early dismissal schedule today. So I'll leave this screen up while I talk about the reminders. So if you need to take a picture of this, you can. So classes are just under a half an hour. Our first period is exactly a half an hour. Otherwise, they're just under or just, no, they are a half an hour. Okay, just kidding. They are a half an hour. We have this like break during the morning, like 15-minute break, and then we keep going. So there's no lunch for you guys built into the schedule today because you're done at noon. So some other reminders, again, Chapter 13 Mastering is due next Thursday. Hopefully after this week, you have at least half of it done. The Chapter 12 and 13 quiz will be next Wednesday for everyone. So it's 20 multiple choice questions. So whether you are at school or whether you are at home, you will take the quiz on Wednesday. So you can make yourself a note of that. We have already covered everything that's going to be on the quiz. So yes, you're going to have video 14 to watch, and there will be a short video 15, but that will not be on the quiz. Again, all recordings continue to be added to the playlist. And then just a quick reminder, it is Green Day on Monday. So Monday is a Green Day. So I will see those of you in the green group on Monday. Otherwise, I'll see you guys online. So let's switch over to mastering. So if you just have a blank piece of paper that you want to work through mastering on, I have typed out the question just so that I can work through it. And I actually have this short link that I will share with you guys as well, in which I've worked through all of the question already. So if you want it just to reference, I'll put it in the chat. So there's number 23 of mastering as well. But I'm going to go through, I'm going to talk through it, and we're going to actually look at some parts of the questions that a lot of people will have questions on throughout all of mastering. So number 23, again, I just typed it out on a piece of paper so that I could work through it right here. But again, this is number 23. So your numbers will probably be different. Your density might be the same, but the mass of H2SO4 is probably different because I just made this number up. So sulfuric acid, a sulfuric acid solution containing 551.7 grams of H2SO4 per liter of aqueous solution has a density of 1.329 grams per centimeter cubed. Okay, so I'm going to work through this information that was given to me first before I worry about doing any calculations. So a sulfuric acid solution, so that's telling me that sulfuric acid is the solute. So I'll use a different color here. 551.7 grams of H2SO4, there's my solute. Per liter of aqueous solution. So if we read that carefully, per liter of aqueous solution, we have 1 liter of total solution. And that solution has a density of 1.329 grams per centimeter cubed. So we know the solute, but they didn't tell us what the solvent is. Remember, for acid solutions, so whether it's HCl, H2SO4, HBr, if you have a solution and the solute is an acid, the solvent is water. So they didn't outright tell us what the solvent was, but we know that it's water. So now we have all this information, the solute, we have the total amount of solution, we have the density of the solution, and we know what the solvent is. So for part A, calculate the mass percentage of H2SO4 in this solution. So we want to calculate mass percent. So mass percent of H2SO4 means we're going to have the mass of H2SO4 over the total mass of solution times 100. So mass percent of H2SO4, that's the mass that goes up on the top. So I know the mass of H2SO4 because they told us in the problem. So 551.7 grams of H2SO4. I need to figure out the total mass of solution. Well, I know that we have 1 liter of solution, and I know the density of the solution. Something else to keep in mind, centimeter cubed is the same as milliliter. So centimeter cubed is the same as milliliter. So grams per centimeter cubed is grams per milliliter. And so what we can do is we can take, so over here off to the side, I'm going to take 1 liter of solution, and I need a way to go from volume of solution to mass, and I can use the density. So 1 liter is 1,000 milliliters, and I can go from milliliters to grams using the density. So for every 1 milliliter, because it's 1 centimeter cubed, 1 milliliter, 1 centimeter cubed is the same. So for every 1 milliliter of solution has a mass of 1.329 grams. Your density might be the same. I think I just read the density off of the problem. So you might have the same density, just your mass of H2SO4 is different. So 1,000 times 1.329 is 1,329 grams of solution. So now I have mass of H2SO4. I have mass of total solution. Times 100. So I put in parentheses how many sig figs we need to round our answer to. 551.7 divided by 1,329. Don't forget to multiply by 100 because it's a percent. So 4 sig figs, 41.51%. Now, your numbers are probably different. I think my original amount on 23 was 571.8 grams of H2SO4. So I changed it just to make sure that I was doing something different. So assuming you had something around 551 to start, you'd have something around 41.51. So this is just calculating mass percent. I will tell you on a lot of the mastering questions, it's not just an outright, here's grams, solve. You might need to solve for grams, but you're using molarity. So you have to solve for moles and then grams. There's a lot of conversions that you have to do for this mastering. But that's how it is for AP. So for part B, calculate the mole fraction of H2SO4 in this solution. So calculate the mole fraction. So mole fraction is represented by a capital X. So mole fraction of H2SO4 means that we have moles of H2SO4 over total number of moles. Remember from yesterday that means that we have moles of solute plus moles of solvent. We looked at that yesterday. You have to solve for the moles of each component and add them together. So we already, no, we haven't solved for anything. Okay, so over here off to the side, I'm going to solve for moles. So I know my solute, 551.7 grams of H2SO4. That's my solute. Well, if you look at this and you're like, well, how much solvent? Well, here's our total mass of solution. Solutions consist of solute and solvent. So if this is the solute, the rest of it must be the solvent. So 1,329 minus 551.7, 777.3. And remember, the solvent is H2O. Solvent is H2O. So again, to get the solvent, I did the total mass of solution minus the mass of my solute. Solution, solute. So now we just need to go to moles. So I'll give you the molar mass. I calculated them this morning. Molar mass of H2SO4 is 98.076 grams per mole. And then water is 18.016. So if we look at H2SO4, remember, keep it out to at least 4 or 5 sig figs. 5.625 moles of H2SO4. And then 777.3 divided by 18.016, 43.14 moles of H2O. Now you look at this, you're like, well, does it make sense that I have so much more water? Well, yeah, it's the solute, right? Or the solvent. H2O is the solvent. You always have more solvent than solute. So now we can come back over. I'm going to split this in half. And I can plug everything back in for mole fraction. So mole of H2SO4 is 5.625. Total moles, so make sure you have parentheses on the bottom. Solute, 5.625, plus solvent, 43.14. And then plug in your calculator. Don't forget the parentheses on the bottom. Three sig figs, so 0.115. Remember that mole fraction does not have units. So this problem required us, just like yesterday, to go from grams of our solute and solvent to moles. So then for part C, calculate the molality of H2SO4. So molality is moles of solute over kilograms of solvent. So again, in mastering questions, there will be some that will say, if you have a 0.5 molal solution with 1,000 grams of solvent, how many grams of solute could you have? You need to make sure everything is converted. Use the molality equation. You'd solve for moles, and then you'd go to grams. So you have to make sure to use any of these equations. Make sure your units are exactly what they need to be, and then you might have to convert back out after. So for part C, calculate the molality of H2SO4. So that means I need moles of H2SO4 on the top, kilograms of solvent on the bottom. So solute is H2SO4, solvent is H2O. Moles of solute we've already calculated. We calculated H2SO4 over here. So 5.625 moles of H2SO4. Now I need kilograms of solvent on the bottom. Well, I haven't found kilograms of solvent, but I did find grams of solvent. So remember, just in case, 777.3 grams. There are 1,000 grams in 1 kilogram. So there are 1,000 grams in 1 kilogram. So I can put kilograms of solvent on the bottom, and we can divide. 5.625 divided by 0.7773 4 significant figures. 1, 2, 3, 4. I'm going to round to where this 6 is. Your answer is not 7.236. That 6 should round up. 237. And your units are either this lowercase m for molal or moles per kilogram. Okay, and then finally part D, and this is usually where people have the questions. And for part A, because when you calculate molarity, you need moles of solute over liters of solution. Well, again, moles of solute we've already found. 5.625 moles. Then we need liters of solution. If you read the question carefully, it says per liter of solution. Per liter means 1 liter of solution. So there's our molarity. That's why it's useful. Notice how the answer wanted 4 sig figs. I already had 4 sig figs. So this 1 liter came from the problem. The problem said 551.7 grams of H2SO4 per liter of solution. So make sure you're reading the questions because sometimes that gives you how much solvent you might have as well. And then one other quick hint I wanted to give you was for 28. So down here at the bottom, for number 28, it's talking about brass, which is an alloy. And it says that a particular sample has a certain percent of copper and a certain percent of zinc. So the first tip I'm going to give you is just turn percent into grams. So truly, just like with empirical formulas, drop the percent and make it grams. So if it's 80% copper, it's 80 grams of copper and 20 grams of zinc. And then it gives you the density. So it gives density in kilograms per meter cubed. If you divide that density by 1,000, that gives you density in grams per centimeter cubed, which remember is the same thing as grams per milliliter. So that's just another hint for 28. You'll need the density. So just divide the density that's in kilograms per meter cubed by 1,000. That'll give you grams per centimeter cubed, which will be the same as grams per milliliter. So any